So of course in this unit we're talking about matter. And as a chemist, the matter we usually encounter is either a solid or a liquid or a gas. And we know some things about that and what it implies. For example, we know that solids have a fixed volume and a fixed shape, and solids are generally incompressible. We know that liquids have a fixed volume, but they have a variable shape. They take the shape of their container. So I can have a short, fat glass of water and a tall, skinny glass of water that actually have the exact same amount of volume. And liquids are generally also incompressible. The last thing we know, of course, is a gas, and a gas has no fixed shape, no fixed volume. It takes the shape of its container. And gases are compressible. Well, that's a whole lot of words, but it would be nice to have a way to represent that I could look at. And one way that chemists do that is by what's called a particle or particulate diagram. And particle diagram is a mouthful, so sometimes we just call them matter maps, especially right now, because we're really looking at what does this diagram tell us about matter. And matter maps are adored by test makers near and far, including all those wonderful folks who write the test for College Board. And so we want to make sure that you have encountered them early and often. The reason that test makers like them so much is that they give you a chance to show your understanding of what being a solid, say, means on the atoms or molecules that make up that solid. And it's also a way of having us think like a chemist. What's going on the atomic level, on the molecular level with the substances that I'm studying? The problem is that any scientific model is going to have some simplifications and limitations. So matter maps, being a scientific model of what things look like on the submicroscopic particulate level, they have limitations, and there's two really important ones. So this matter map is a matter map of a gas, and if I think about how I could tell that, well, using my lived experience is a good idea. We know what happens if I put a solid in a container. It sits on the bottom of the container. We know what would happen if I pour water into a glass. A glass is just a container, and the water sits on the bottom of the glass. Only in a gas does the matter fill the available space. So this is a matter map of a gas because the particles are all over my background. But there's two problems with this matter map of a gas. One is that I have obviously scaled up the size of the atom in this gas. And if I scale up that distance between the atoms the same way that I scaled up the atoms themselves, this matter map would have one dot in it, and the next one would probably be down in Mr. Moore's room or down in Mr. Pulliam's room on their board. And one dot is not a helpful matter map. So we had to concede when we made our model that we could scale up the size of the atom, but we would not scale up the size of the distance between atoms or molecules. The other thing is that a matter map is like taking a picture. If I go take a snapshot of a race, I'm going to get all these people running as fast as they can, but my picture is just going to be that one still second. I know that right before the picture was snapped, they were running. I know right after they were running, but all I have is my one still snapshot. So with a matter map, it's just like a snapshot. It's one instantaneous second. These particles should also be moving, and in gas particles, they should be moving really fast. And even in a solid and liquid, the particles are still moving. but I can't really demonstrate that with a particle diagram. So here's an example of a matter map or particle diagram. So let's think about what we can decide from this down here. So what would this be? A solid, a liquid, or a gas? Well, using what we were just talking about on the last slide, it's probably not a gas because it's not filling the entire container. It's just sitting on the bottom. So I can take that out, and then I've got to think about, is it a solid or a liquid? These particles are very close together and packed together very regularly. So I think that this is far more likely to be a solid, something rigid. It doesn't flow or move like a liquid does. So draw yourself an example solid matter map in your notes if you haven't already. This is a solid element. We'll talk about that a little bit more in just a second. But solids, what do I need to see if it's a solid? I need to see that the solid is at the bottom of the container. I have to see that the solid is packed together very tightly and regularly. And this is also a little limitation with matter maps. Not every single solid is packed very regularly, but it's the best way for us to represent it with this simplified model. So now, let's think, is this a pure substance, an element or a compound, or is it a mixture, a heterogeneous or homogeneous mixture? Well, I look at all these little particles down here, and all these little particles are the same. They are the same size, they are the same color. So that tells me it must be a pure substance. And then I have to think about the definitions here. An element is all one kind of atom. A compound has more than one type of atom in a definite composition. It has the same ratio of the atoms over and over and over. So since this is only one kind of particle, this must be the matter map of a solid element. In reality, remembering that this is a model and models have limitations. In reality, if we could see them like this, they wouldn't just be sitting. They would be vibrating. Because what we know is that all solids have some kinetic energy. If I think about my little video here, this would really be more what a solid would look like. You can see all of these particles are just vibrating near each other. So this is a little audience participation break. You take your hands, you put them next to each other so they're nice and close together and touching, and then you vibrate them back and forth. And now you have a little tiny reminder of what's going on in a solid. So moving on from solids, we can think about liquids. Liquids are variable shape, so they have to be able to move and kind of flow around each other, unlike a solid where it's just stuck in one place. But liquids still sit on the bottom. Think about the water in your water bottle. So we see them close together on the bottom of the container, but they have some degree of movement or freedom. It's not all crammed together in a nice orderly solid. So you remember that this was your solid. Then to show that we've got a liquid, those liquid particles can flow and move. So you can see my hands are showing that the motion of those molecules is flowing and moving and tumbling around so that they can take on the shape of their container. Again, it's a model. It's a simplification. This is an instantaneous moment in time. If I really want to look at what's going on a molecular level, they should be in constant random motion. But you can see how even in this video clip of the simulation, they're still close together on the bottom, but they're not all regularly stacked. They get to move and flow and tumble. And we talked a little bit before about what a gas will look like. So here is another picture of a gas. The particles are far apart. They're all throughout the container. And again, we have the problem of this being a model, remembering that the distance between our particles would actually scale up to be much bigger than this, and that they too are in constant, random, rapid motion. We have a whole unit on gases this year, so we'll hear a lot about that in the course of the class. So remember, if you can use your body to remind yourself of these things, you have a solid, you have a liquid, you have a gas. The gas is in constant random motion, it's everywhere. So all of those were elements. They were all one atom of one substance. So what could I do if I had a compound? Well, if I have a compound, I have to remember that the definition of a compound is that it has two or more different elements that have a definite composition or a consistent composition throughout. So looking at this compound, it's clearly three little greens to one big pinky yellow. And every one of them has that same ratio of three greens to one yellow or pink. That's what I mean by a definite composition. Water is H2O. It's H2O here, it's H2O in Russia, it's H2O in Siberia, it's H2O in Pluto, because that compound has that definite composition. So that's how you can really look at a particulate diagram and tell if it's a compound. I see two different kinds of particles and a consistent ratio, 1 to 3, 1 to 3, 1 to 3. So what do you think? If I had this as my matter map, would this be the matter map of a solid, a liquid, or a gas? And if you said gas, you are correct. These particles are far apart. They are not sitting at the bottom. Well, what would a mixture look like? If I have a mixture in a matter map, it's going to be made of two or more different substances. It could be two different atoms of elements. It could be two different compounds. So there will be differences in the particles. And they will not be overlapping each other like this in a compound. So here I have this one atom thing, which pretty much has to be an element, and this 3 to 1 thing that we've talked about being a compound. So what do you think? Are these solids, liquids, or gases? So this is a mixture of a gaseous element, right here, and a gaseous compound. But when we talked about mixtures, we had a thought about homogeneous mixtures and heterogeneous mixtures. So let's think about how we could represent a heterogeneous or homogeneous mixture as well. So here's a liquid mixture. I can show that they're close together. They're sitting down towards the bottom, but they're not all nice and regimentedly placed on the bottom. And so what I want to think about when I look at a heterogeneous or homogeneous mixture, of, say, something like a liquid element and a liquid compound is I want to look at this and say, are these together? Like, are they mixed in together, or are they in layers or sections? Now, these are all, there's a compound and the element, and the compound and element, and compound, element. This is a homogeneous mixture of a liquid and element and a liquid compound, because if I zoomed back out, I wouldn't have any regions of just element or regions of just compound. It's all mixed together. I would have to be able to zoom in to the molecular level to be able to see this individual difference. So let's put it this way, folks. We're not out here trying to be evil. Do not overthink it. If I have a particle diagram or matter map and I'm trying to figure out whether it's heterogeneous or homogeneous, I am going to know that this is not the easiest thing in the world to depict on a matter map. So you will see distinct individual layers of a liquid or a gas floating on top of a solid, something where you will not be going, oh, is that big enough to be a region? I mean, yeah, there's 3 little gray guys here. Okay, well, you can't see 3 atoms. So it would not make sense for me to put 3 atoms together and be like, oh, they're going to know that's heterogeneous. It's going to be obvious. We're not out here trying to be evil. Ooh, all right. So we're into some practice problems. Let's take a look at this one. And I'm going to let you pause the video and draw this out and write down your guess as to what you see for practice 1. All right, so I have a gas up here. You can tell it's not at the bottom of the container. It's widely spaced apart. And this is still a compound. I can tell because I have 2 different colored spheres and they have that consistent ratio of 1 to 3. So there's a gas on top. Now if I look down at the bottom, this is clearly different from what's on top because this is all just orangey spheres. It's on the bottom, not a gas. It's very ordered and regular. So that makes me think solid. So how do I put this in kind of a sentence? Well, I say I have a mixture of a solid element and a gaseous compound. And then since I'm talking about mixtures, I want to put a fancy word that starts with H on it. Are these mixed together? No. The particles do not show them being mixed together. It is this by itself and this by itself. So this is going to be a heterogeneous mixture of a gaseous compound and a solid element. All right, so now let's take a minute and look at practice 2, and I will again let you pause the video, think about it, and write down your thoughts. All right, well, first thing I noticed is that every single one of these things is the same. Every single one of these things is the same, which means it's all one type of atom, which means I must be dealing with an element. So now I can think about my phases of matter. I have a few gas particles up the top, and I have a lot of particles down at the bottom. But I notice that these particles are not just regimented, evenly spaced, they're clumpy and lumpy. So in this case, I can say that down here, the bottom of this appears to be a liquid over a solid. So I can say I have a liquid element and a gaseous element, and it's a pure substance, it's an element. This is actually something that really happens a lot It's called the vapor pressure of this element because some molecules are going to sneak off into the gas phase and start filling up the top of your container just by virtue of random chance and motion. All right, so let's try practice 3. Oh, okay, I have 2 different things again. I have red circles and yellowy orange circles. So I know I have a mixture. I have 2 different things. So if I look at this, all of these red ones, there's not 2 things in constant ratio. So I'm going to call this red an element. So I have a gas and a liquid element mixed with another liquid element. And since I'm thinking mixtures, I want to think that fancy H word. And I look at this, and if I zoomed out, I could see a whole big strip here of these red element particle diagrams. So this is heterogeneous. Again, like I said, it has layers, oil and water. So here's practice number 4. So now I actually, it appears, has 3 different things in here. I have the red circles, I have the orangey circles, and I have this, which seems to be coming as a unit, and it comes as a unit of 1 blue, 1 green, 1 blue, 1 green, 1 blue, 1 green. So I have a compound here. So I have 2 elements and 1 compound. And now I need to think, what is my state of matter? Well, not all sitting at the bottom, so pretty much has to be gases. And then I want to think, is this heterogeneous or homogeneous? Well, these are all mixed in together. There's no distinct areas that are just one kind of particle diagram. So I would say that this is a homogeneous mixture of 3 gases, 2 elements, and 1 compound. And here's our last practice problem. All right, again, I am going to take a look at this, and I notice these are kind of touching, so I'm going to take a look and make sure that we have, we don't look like we've got a compound here. Well, these 2 aren't actually quite overlapping, and this one would be overlapping with 3, so it does not look like I have a consistent ratio here. So I think I will call this 2 elements. They're at the bottom, but not stacked all regularly, so 2 liquid elements. And I see that these are scattered throughout, so I think I can say a homogeneous mixture of 2 liquid elements. So you kind of see how these are going to really help us focus in on what does it mean for it to be a solid. It means that your particles are tightly packed together. What does it mean if it's a liquid? Your particles can move and flow, so they're not just stuck tight together. And what does it mean if something's a gas? It means that your molecules are moving like crazy rapidly throughout the whole space. And we can use our particle diagrams or matter maps to draw a little snapshot in time to help us understand what's going on.